informatics problem. And all this generates model for anticancer drug design. Hanna will show. I would like to say for the people who are confident that our organizers, they just put all this presentation to YouTube, and so some people also have the opportunity to be members in online mode of our community. So please.
Good afternoon, dear participants of the conference. Today will represent the work of our team. So mostly, you know that machine learning is very famous in this area like Informatics, Informatics, and also now it's very popular in medical chemistry. So I would like to know what we make with our team in that area. How you can go to the next slide?
Scroll.
Okay. So, chronic leukemia is an important problem for society. The first is because currently we don't have available drugs. All of these which drugs we have high toxicity and resistance. And that is very actual, especially for the donors and for the all European countries. The chronic leukemia is mostly the disease for the people with the old ages. So, my speech today will be separated on the two main parts, which you can see on the slide. It will be drug target discovery, lead generation, and validation. So, in our project, we would like to build a deep-generative model, which will be able to generate new ligands against leukemia. Our goal was to find most effective and non-toxic compound against ML, which will have the pyrimidine in their structure. So let's go into it. So for the first, we must need to identify the molecular target in which we will be focused on. The current leukemia is activated by the some proteins, and from the mutation in the genome is activated from the kinase proteins. We would like to focus on the bacterial kinase structure you can see on the slide, and on the most popular mutation of this. Myeloid leukemia have 21 mutations, and T350I is the most popular mutation. That is why we would like to find compounds which will be active to the both of them. So after we was needed to make our molecular library, our map. I also mentioned at the beginning that we want to find compounds which will be based on the aramine pyrimidine. That is why we will use a subchem dataset. They were promoted from their 120,000 compounds containing aramine pyrimidine. After this, we will need to make for our neural network the representative which will be usable. For the first, we had two string-based formats, which was mouse and canonical smiles. It is the text representation of the compound. And also we made molecular document that compounds with the after-document. Molecular document was made with the fixed receptor and flexible ligand. And also we had on the input ligand reception binding energy, which was added to our neural network. So what was this? So our neural network is a classical heteroencoder. Which has 3 inputs and 2 outputs. On the inputs, we will have our smiles, canonical smiles, and also we have vector with the features, which was included such information like large base of molecular, roles of Lipinski, visibility. So, and on the output, we have the two formats that was smiles and canonical smiles. So, the structure of our neural network was looking like presented on the smiles. So unfortunately here some project, but it's still possible to see. On the input, as I told before, we had our smiles and canonical smiles, which was going to the LSTM encoder, and after that was going to the dense encoder. So also in the input was our features, which was directly going to the dense encoder. On the content layer, we was add our energy from the molecular document, which I added and as an output, we still have the performance that is smiles and canonical smiles. So the training size was 25 approximately. So as we see from the graphical support function, we can say that our neural network works correctly and don't have retraining. From this, we can make decisions that our network works correctly, indeed we can get the results from this. So, and which results we have? So our neural network was generated 1083 unique compounds. It was not only compounds, which was really good. So it was limited to compounds who has energy less than -9. This is my main exploration here, as you can see. So, and with this compounds, we will work after this. So how we make the validation after generation, we made again record of experiments on the same route as it was on for the input. So we will need to choose a really special compound. For this, we will decide that we will use this for the function as after the and as for 2 and as for 4. From that function, we will get 569 compounds, which have energy less than -5 of the experimented after the and after being calculated by the energy for all the expert function, make corresponding to them. From that our experiments, we choose it for the best compounds. So this compounds you can see on our slide in the blue frame, and you can see our control is Konstantin. Konstantin is already working drugs against Leukemia. As you can see from the information, so our compounds is also not towards the Konstantin, so we can make the future research with them. So there will be the next that I would like to tell that we have a good decision. We have a good approach for our law, and we will continue to make the research with making molecular dynamics and the future research in the compounds. To see if they really fail, it was really good results, and if they really can become drugs. So thank you for your attention, and I'll be glad to answer your questions.
Okay, please. No question. So maybe because it's necessary to ask at least one question. But why do you use these three inputs instead of one? Is it one is not sufficient for you?
We decided to use 3 inputs because, as you know from the literature, it's still the better results, and we will have a better input if we will use a different style of the input. So then we will have more better compound, and as you can see as a result, from current information, it's really good. So I think we made a good decision for the next 3 inputs, not only one.
Have you verified this? For example, if you use your just smiles representation, you can get also these 2 histograms, and just to see that if your compound generated by your model with 3 inputs is really better in generation compounds.
So at the beginning of our work, we was trying to make 2 inputs. It was inputs with smiles and feature information. But we saw that the better results we get when we have really 3 inputs. And that's why we decided that this will be the best approach which we can do with our work.
Okay, thank you very much. There are no other questions, so we once more and go to the next presentation. Next presentation is by Gonchar, who is also from United Institute of Informatics Programs, and the title is just application of semi-supervised GAN in combination with JT variational encoder for generation of small molecules of this kind.
Good afternoon. So you see the slides with you. I will present to you our team's work, like application of as GAN. I will call it later as GAN. and junction tree with this combination of junction tree variation of the blood. So. Okay, this problem I'm going to solve. This is tuberculosis treatment. We know that in 2020, according to the World Health Organization report, 1.5 million people died from tuberculosis. It happened due to the COVID-19 pandemic, but also we also know that the tuberculosis treatment nowadays is pretty strict and long process. Each year, the number of drug-resistant Mycobacterium tuberculosis strains is growing. Therefore, the problem of tuberculosis treatment is extremely difficult and actual for scientific society. Okay. In our work, we are going to use a strategy like called de novo design, with using of deep generative neural networks. But the idea is to choose a protein target involved in important processes of Mycobacterium tuberculosis cell and block its activity that causes the death of Mycobacterium tuberculosis cells. Also, for computer-aided drug design strategy, we need the specific information about the protein target we are going to choose, the 3D structure of this protein, also known as inhibitors of this protein, and mechanism of action. Our team decided to focus on blocking the formation of outer layer of Mycobacterium tuberculosis cell wall. And among the promising targets involved in the process of the synthesis of nucleic acids that are formed the cell wall. Yeah, we choose KasA protein. KasA, beta-Keda acetylase 1, because it meets all the requirements we set previously. Like we have a 3D structure, know the inhibitors, and also the mechanism of action of KasA also described in the literature. Let's go to the neural networks part. So we know that small molecules are represented in a computer with two techniques, like linear annotations and graph representations. But linear annotations has a drawback in generation models. It is that generative model can generate invalid strings, but graphs are always generated in proper way. Yeah, therefore we decided to use graph representations for our work. But graph representations also have some disadvantages because nowadays the generative adversarial networks models which use graph representations directly also I know several maybe. Therefore, we decided to transform our graph representations into graph embeddings and feed it to generative into GAN. For this purpose, we used junction tree variation autoencoder, a pre-trained neural network. So we can see this scheme that in bottom our junction tree wire and the latent vector from it used to train discriminator of S-gun. So during the training process, we feed true data like from training set and also the noise, random noise from Gaussian distribution. What's the meaning of semi-supervised jump? It means that you can see a discriminator output. Usually, discriminator can predict only one thing, like if molecule if molecule is real. It means if gun generate a part of gun generate a good molecule, so it is similar to real or not. We added the second output, which predicts to which class of energy our molecule belongs. How we obtain the energy values? We used a molecular dot. So the process of training set preparation, we use PRIP and pharmacophore models to collect the compounds similar to telecomycin and its analog T11-5. They are known inhibitors of KasA. And then carried out a molecular docking to obtain the energy and the energy class. And after that, we feed all these compounds into junction tree wire to obtain the latent vectors of compounds. We can see the distribution of docking values of our training set, and also molecular weight of molecules. Okay, and this is the graph of training of S-gun. So we train it in 50 epochs and train our generator more than discriminate. And after training was completed, we feed Gaussian, we feed random vectors from Gaussian distribution to it and look what prediction the discriminator gets. And we can see the promising area where the probability of low binding energy class is high, and also probability of data reality better than half of our vectors. So we decided to generate new molecules from this region. Also to check if our neural network works properly, we choose vectors from unpromising region. You can see the conditions in the table, and there were a lot of duplicates because the junction tree variation autoencoder works on graph representation, and it is difficult to separate vectors located in latent space in little near each other. And after generation, we checked we do docking once again for generated compounds, and we can see that in our promising region, average binding energy was lower than our border, and 87% of generic compounds were better than the border we choose. And in the end, also we estimated our complexes updates from molecular docking by other 3 functions, score 4 and NN score 2, according to additional to autodoctrina, and choose. You can see the values for the best 6 compounds that we are chosen. They are much better than our control inhibitors, TLF5. So, but because molecular docking isn't has some errors, we need to investigate these molecules with molecular dynamics. And they're going to do in our projects, next project. Thank you.
Okay, thank you very much.
Please return back to the slide number 7 and give more details concerning data sets.
Number 7? Yeah?
What data were used for the trade, for selling trade?
Okay, there was 50,000 of molecules which we obtained from PRIP that is similar to our inhibitors. And we produced the latent vectors from by junction 3Y. And also this set we added the similar number, 50,000 of random generated vectors from Gaussian noise. And but not from Gaussian noise, I mean like this from Gaussian noise they are fit to generate and да, хорошо. Получается, вот здесь вот, когда мы дискриминатор передаем вектора, у нас было ровно 50 тысяч тех, которые хорошие, и столько же тысяч только тех, которые генерировал генератор. То есть, чтобы было одинаковое количество. Как fake data, так и real data.
Здесь есть тонкий момент. С одной стороны, нам нужны такие вектора для тренировки, которые обладают определенными свойствами. То есть мы уверены в том, что они дают нам нужное качество. А с другой стороны, вот случайно мы их можем как бы аргументировать, но изначально нам нужны эти книги откуда получить. Вот. Может быть, они откуда-то еще взяты из других методов.
Нет.
Ну хорошо, ладно. Это может быть далеко мы уходим от темы. Спасибо.
Хорошо. Еще есть какие-то вопросы? Yes, no? Okay, so thank you very much. So the next speaker is in our session is Yuxiang Chen, who is a postgraduate student at the Department of Applied Mathematics and Computer Science of Belarusian State University. Please, Yuxiang.
My subject of presentation is the identification of picture combinations in Genome-Wide association studies. Association of single nucleotide polymorphisms with traits is widely used in Genome-Wide association studies. However, identifying meaningful SNP combinations can be challenging due to redundancy and complex trees dependencies. In this study, both computational approach to reduce SNP's redundancy using feature relevance. We apply this approach to identify drug resistance mutation in bacterium tuberculosis strains and achieving accuracies range from 65% to 90%. Genome-wide association studies aim to find single nucleotide polymorphisms associated with phenotypes. Traditional methods they focus on individual SNPs testing, and they ignore complex traits often involve multiple SNPs. In our method, we use the feature relevance to reduce SNP redundancy and improve the computational efficiency. About GWAS problem, first, each GWAS, each sample is a genome and consisting of 4 nucleotides. And for each drug, the sample can be divided into drug resistant and sensitive. GWAS problem aims to find the association between SNP's matrix and phenotypic matrix. About data set, we collect data from the TV photos. They supply the sample's genomes and their drug resistance information. We use the 20 drugs for this test, and max was set to 5%. After filtering, the SNPs was 3,392, and samples was 3,108. About picture set reduction, we used max relevance and max distance. Giving a sequence of SNPs X, it can shorted by accuracy value. This part is relevance, and then calculate each SNP pairs, and this distance can use Pearson relation coefficient or another. In this time, we use the Pearson correlation coefficient, and the third step, we calculate evaluation value for each SNP pairs using this formula, and then select the subsets XQ of relevant SNPs, and then calculate the accuracy value for of the data set. And this table, table 2 and table 3 show the result, best accuracy and their SNP combinations. And table 2 showed the first line drugs results, and table 3 showed the second line drugs result. In this study, we address the complexity of tools by redundancy SNPs using feature relevance. Our approach effectively identifies SNPs combinations associated with drug resistance in Mycobacterium tuberculosis with accuracy ranging from 65% to 90%. The search offer values insights into TB treatment and highlights the potential of mathematical technique in genomic studies. Our data is collected from this program, and the detailed information to the this website.
Okay, thank you very much. Please, do you have any questions? Because this report in some ways correlated to the presentation of the previous sections, but also our colleagues, they used this relevance of features, which is in some way opposite to similarities, to create some redundant set of features also. But here we use it for approach to related to like finding some subset of features which are important for diagnosis of drug-resistant tuberculosis, but in some way they are like similar in approach. Are there any questions to our colleague from China, which has a PhD study in our university? No? Okay, thank you very much. Then maybe the last question I will ask. So what you plan? What is your approach? So you will just do this relevance feature approach, or you have something additional in mind to test for to find this redundant set of features?
I'm not clear.
So you did this approach based on redundancy values, right? To find a small set of features.
Yeah.
Yes, but other approaches I described in the literature, how it's possible to reduce this set of features. Do you have in mind some other approaches also to use?
This step, in this step, can change the greedy algorithm and to find more combinations. Because in this way, so we only test 50 important SNPs and find their combinations. And some SNPs will be filtered by step 4. So greedy method maybe have a better result.
Okay, so you have idea to use several algorithms and then to select these combinations of features which are best among these several algorithms, right? Okay, thank you very much. So we have the next presentation. It will be done by MikalaiYatskou and his colleagues from Department of radiophysics and computer sciences and biological department of our university. Okay, please. I would like to say that MikalaiYatskou is the department head the faculty of radiophysics and computer technology.
System analysis and computer model, yeah.
Yeah, okay, please.
Good afternoon, dear chairman, thank you very much for kind introduction of my talk. And I would like also to thank the organization for giving us the opportunity to present our talk. Our recent results, which were done in collaborative work in the Faculty of Radiophysics and Computer Technologies and Biology faculty. So, the title of the work, simulation model for machine learning and identification of single nucleotide polymorphisms in human genomes. So, as a logical consequence, my work is quite on the same topic as previous talker, Mr. Chen, and I hope auditor is a bit keen on this topic, and maybe it will be a little bit more easy to introduce the problem of SNP identification in DNA molecules in bioinformatics, which is quite a big question. So, single nucleotide polymorphism, the abbreviation is SNP, which I will use later in my talk. One common types of genetic variation in the human genome, and what does it mean particularly? If we have, for example, this is part of, let's assume that this is molecule, yeah, and this is sequence of nucleotides, and you see one nucleotide, yeah, G, which is shown here as one nucleotide. When it's changed to another type of nucleotide, like here it's shown in red color, then it's called SNP or single nucleotide polymorphism. So and this is a problem which we would like to do and would like to improve the results which we are in up to now. So what are the traditional approaches which are used in this area? So I would say quite plenty of statistical methods. So based on binomial distribution, entropy-based test, Fisher test, and nowadays also modern algorithms of machine learning are applied, like neural networks, but not so many work have been done up to now, and mainly not in humans, but in. So this methods quite universal and simple for program implementation. However, they are computation to be used. One analysis of experimental data with high level of knowledge for various experimental dispersions, which can introduce gaps, insert or deletions in the nucleotide sequences. So this is quite a problem, and if we are talking about genome sequencing equipment used in our work, our countries, so this is quite typical of our research areas. So what I would like to say that simulation modeling is also used in this area, and for several reasons. So it's used to select most optimal SNP identification algorithms because it's very often it's quite flexible, and to test competing plans or method of analysis, and to evaluate performance of specific experimental design, and also nowadays simulation model also used to form or to generate data, training data which can be used for training machine learning algorithms. So this is quite interesting subject on which we would like to concentrate our work. So there are plenty of simulation models which are used to simulate SNP sites in the DNA molecules, and they are based on a different approach, namely some parameters of experimental equipment, use of different probabilistic models, also auxiliary biological information, and so on. However, this method have only few modeling methods use experimental results and complex simulation schemes. So as with a particular probability distribution and based on the generated data, we can create a machine learning algorithm or use classical algorithm. This is done in block number 4, where we apply proper S&P identification algorithm and we can find S&P size. So we go to simulation model, which we propose in our work idea of this model in front of this block scheme. So we simulate sequence of nucleotide, position in each position can contain S&P or not S&P size, and they are generated according to beta or Gaussian distribution. Beta distribution we took from literature, and Gaussian distribution is quite logical step also to test, and more complex distributions have been also verified and tested. So I don't go deep in this scheme. So to validate our numerical algorithms, we took some publicly available data. So our reference data were on human chromosome 22, coming from GIAP consortium, and this data set contained nearly 30 million of nucleotide sites, of which were more than 36,000 were S&P. And here you can see how does it look the data set. Yeah? So the name of site, then we have reference site, and a channel for nucleotide A, C, G, T, and they represented numbers of covers or reads which are available from genome sequencing experiment. As this number is higher than experiment is more accurate. So first, we investigated the experimental data. We analyzed histograms of total number of coverage for data channels, then maximum number of coverage, and difference between maximum total and the maximum number of coverage. We can see the distribution of experimental data. Top 2 figures for non-S&P sites and bottom 2 figures for S&P sites. And approximations made by vector distribution black line and Gaussian distribution are shown here. Yeah, so vector distribution is a bit better into the data than Gaussian distribution. So our conclusion we use for simulation model the vector distribution is optimal, and number distribution is less accurate. But probably for other experimental techniques, Gaussian distribution can be used. So next, we developed, we tested simulation model, and we simulated 10,000 nucleotide sites with parameters of beta on normal distributions. And these distributions were quite nicely approximated by a proper beta or Gaussian distribution function. We can see this distribution, histograms of simulated data, and smoothed out by beta and the Gaussian distribution functions. So we recovered the parameters which were put in simulation model. So the next step was to make a comparative analysis of most famous or most effective assembly identification algorithms, and also to compare with machine learning algorithms which were trained on our simulated data. So we selected binomial distribution test, entropy-based feature test, and for machine learning algorithm, we selected two decision trees methods. So one was algorithm for conditional inference trees and PRIP algorithm. So why this algorithm goes for our opinion was quite good algorithm from this group of math. So we made vectorization, new vectorization of features. So we rearranged the features and inside of X1 is the number of coverage of the record, and from X2, X3, and X4 is the numbers of coverage for non-recurrent nucleotides, so sorted in the standard order. So we selected 5 data sets with starting compositions 3, 9, 15, 21, 27 millions on this chromosome 22, and we analyzed with 5 methods of entropy-based algorithm, binomial distribution, Fisher exact test, conditional test, and current. So what was surprising is that machine learning algorithms they overperformed traditional algorithms. So the best up to now algorithm was Fisher exact test with 77.1% accuracy in terms of measure F1. Yeah. So, but the best estimate we obtained was 82.8, so it's nearly by 5% accuracy higher than of traditional methods. For the Karpenka rate is also high, but not that significant. So it means that our simulation model helps to improve accuracy of SMP identification compared with classical or traditional algorithm. So I'd like to make use of conclusions. Approach the simulation model of SMP DNA molecules is developed. This approach increases the accuracy of the determined genomic sequence of data. So the best results were obtained for machine learning models. The accuracy of SMP identification by the score F1 is the highest, 83%. Rate of simulated data for the algorithm of conditional inference trees. So I'm finished. So I'm open to your questions.
Okay, thank you very much. Do you have any questions from the audience? No questions. So then I would like to ask you a question. Okay, question one. So this like traditional algorithm of finding SNP just have a reference, for example, genome, yes, and you do alignment of your genome with a reference genome and see like the difference at position of nucleotides. And in this case, you just get this SNPs if you have some, but you suggest something different, and I would like, what is why you are not like why do you not like this like traditional algorithm of just alignment? This is alignment procedures, multi-alignment, because you can use alignment with several reference genomes and just comparison. Why you
thank you very much. It's a very interesting question because in traditional algorithm it works very well, but we have also high experimental noise. Yeah. If the signal becomes too noisy, then we lose information because we can make directly underestimate number of size because of the noise. Yeah. And one of the approaches to use this should be application of machine learning algorithm, where we create from one side data set of SNP sites and from another side not SNP site. The frequency of an SNP site is not that high. Yeah, it's like one per 100 sites or 1,000 sites, depending on the algorithm. And we have unbalanced classes. Yeah, so that directly training machine learning algorithm would be quite tricky thing, yeah, because we need to do something to use augmentation or to reduce data set to equal size. This is actually what we did, yeah, but it did not increase the accuracy. So the idea, try to get inside in complete experiment and try to repeat it in our simulations. Yeah, and this is what hypothesis that we would like to test. And actually, it worked well for the system. Okay, going back to the conclusion of your questions, in principle, I expected we have really good data that it should work more or less quite equal. But in case of some problems, I assume this generated data can help to improve the accuracy. And this is actually what we have with our equipment.
Okay, thank you very much for your response. Okay, so the next presentation is will be done by Danilo undergraduate student, or more to say, post-year student of the Department of Applied Mathematics and Computer Science, and this is the his diploma work somewhere, right?
Not so correct, because I would like to change my network, my diploma work.
Yeah,
Well, the same as
yes.
yeah.
Okay, let us.
Okay.
Please.
Hello, everyone. I want to apologize in advance for my voice under the soup. I hope it won't be a problem for us to describe or discuss this presentation. Okay. I want to work in the sphere of rational drug design, and I think it will be interesting for you to know that nowadays the pipeline of drug design is very difficult, and the first part of this pipeline is in silico methods, methods of computer-aided drug design, like screening, optimization of molecules, testing these methods, and given for real biology laboratories some compounds that could be inhibitors in the future. The purpose of my work is creation of new, more effective inhibitor of yeast plus human immune deficit virus of first type. Like you know, human immune deficit virus is very strong disease for our society, and I think it's very important for those to make some more effective inhibitors. Inhibitors is equal to drug. And task of this work is analysis of protein GPs 120 of Keda, making a sample of compounds that can be used to train some neural network. After training, we can generate new compounds with the neural methods, and of course, we can analyze the results of generation with computer-aided methods approaches. Okay, now you can see our protein and existing inhibitor ND 2021. This inhibitor wasn't like our matrix to create new compounds, and with these compounds we make from model is a complex of allosteric and chemical features of our molecule, which we use as the most important features of our model. After making from model, we move to making the first. We're making the first try to make our training set. We use this programs pipeline to use for screening to replicate about thousands of compounds that can be described as potential inhibitors. After that, we make a clarifying document to estimate the affinity of our compounds for our target. It will be needed in the future to describe how our neural network will work. Okay, these are the parameters of our network document. And I think this is the most interesting part for our audience is the architecture of the auto-encoded model. So I can see auto-encoded model with some interesting parts. We use one-hot encoding of the strings of letters which describes our compound. We use one-hot encoding, and after that we use autoencode to make describing of our numbers smaller, and after that we push it down. Okay, and at the higher layer we add built-in energy of our model to make the working space more accurate. And as a training phase, we check the quality of our model, but on generation phase, we give for model only empty distribution, and after that he can imagine what she think about our more effective inhibitor. Okay, so there are some formals. As a loss function, we used categorical cross entropy is quite a simple and useful function for autoencoders. And as optimizers, we used function Adam, which is quite a visual too. There are some results of our training. As you can see, the blue line is training dataset loss, and orange line is validation dataset loss. And as you can see, they are quite near to both of them, and it shows that it's not a problem to train this model. And I think it's more interesting results. There is hidden energy. So there are two histograms of hidden energy distribution for the sample of original compounds and the sample of generated compounds. As you can see, they're quite similar, and our inhibitor JT-VAE is quite at -8 and 2. And as you can see, original compounds and generated compounds is the best results of our model. For example, for NBD 1424, the energy is -8.3. But for our best compounds, the energy is -10 and 0.2. It's quite strong difference, and it's quite good results. And there are some more our results in digits. Okay, there are our parameters for for generated compounds, and try to see results for original compounds and for generated compounds. These are no situations where original energy is worse than generated energy. And as a previous course, we have used ECR, exponential consensus rank, to make a decision what compound is the best of them. We used 3 functions to evaluate our results. It's autopila, error score, and NM score. Autopila is algorithmic method. Error score is error score, and NM score is neural network estimator. And of course, you can see the results for NVD 2024. It's similar, but for this kind of functions, it's better. Okay, that's conclusion. This work, supporting GP's class theory, HIM1, target was analyzed. After that, we made problem for search and clarifying document. And with this information, we're making a training sample for our standard SQL. And so that particular models were trained. We have generated additional inhibitors, and we have identified the most promising additions of them. Thank you a lot for your attention. I will be glad to your questions.
Okay, thank you very much. Please ask me one question, Anna, please.
Yeah, thank you, Neil, for the nice report. Can you please explain to us on the slide 13? It was previous one.
Yeah.
Yeah,
So,
why did you use 3 scoring function? Why not 1?
1 is 1. It's a really interesting question because every approach to estimate affinity of compounds to this target, to their target, have their advantages and disadvantages. And after this information, you should think, oh, but what if we will use advantages of different approaches to estimate affinity? After that, you can make a lot of estimations with different scoring functions, but you will see how we understand which compound is the best. If, for example, the fifth compound is the most has the best results for NN score, but first and second have the best results in graph score. To solve this problem, we can use exponential exponential consensus plan to see the difference in different range and make our decision not in intuition, but in formals and digits. Have I answered the question?
Yeah, thank you.
Okay. Are there any other questions? Okay, please.
One more simple question concerning slide number 9. Calculation functions. We use all in every layer unique calculation function, or they are distributed from the layer from the first to the last layer.
Sorry, I understood the question, but I suppose. Okay. On the downstairs we used glue, on the LSM we used tongue, and at the last downstairs we used sort pass function.
So three different activations.
Yeah. Three different activation functions, but on the some LSM layers and dense layers the same functions.
Okay, thank you very much. Okay, so we have the last presentation. This section will be done by Novikov. Anton is a partial student in the Faculty of Applied Mathematics and Computer Science. So please, 10 minutes, Anton. I know that you usually speak longer, right?
I will do my best. So the topic of my speech is prediction of protein-protein interaction with matrices. So first, we should talk about the notion of 4 levels of protein structure. There is 3 on this page. So basically, first level of structure is sequence of amino residues, which from which protein is built. Secondary structure is the backbone formation. There are like helices, beta sheets, etc. Tertiary structure is the full 3D model of a single molecule, and quaternary structure is a full 3D model of complex protein. So, what is interaction prediction? If we have 2 or maybe more components, here's 2 single molecules, and we know the fact that they do interact. We have to predict how will they interact. There's also distinct protein-protein interactions and protein-peptide interactions. We also usually neglect events, and we neglect flexibility of protein molecules. Here, how to measure quality of our prediction? I use a conservative metric. We fix one of the molecules, and for another, we calculate root mean squared deviation. If this deviation is less than 10 angstroms, then we say that the prediction is correct. So, most popular way to predict interaction is to predict an interface. What is the interface? The interface is a set of pairs of residues which we say interact. So basically, pairs of bonded residues from one molecule and another. So we may predict this interface with some machine learning approach, and then if needed, we can connect two components like it's kind of like solving an optimization problem. One of the methods which we continue in our work, I may say that, is when we have 3D model of component, we take the coordinates of alpha-carbon atoms and build intra-chain distance map. Here's the type. And when we put that map into a fully convolutional neural network, and predict the contact path. There is some also for this approach. It mostly works with homologous complexes. These are complexes which consist of two identical molecules, and we had low accuracy. Right? So we propose another way to predict interaction with rotation and shear axis. So what do we need? We need first to, well, maybe not first, to predict relative rotation of these proteins. Then we have to predict shear axis, basically bonding direction vector which connects centers of both molecules. And then the last step, we have to get a distance between these molecules. We call it the bumping operation. And then we will have our contemporary structure. So to encode rotations and directions, we propose another matrix like encoding, which is also as distance maps. It is rotation invariant and shift invariant. So, in abstract, imagine we have two polylines in some Euclidean space, which consist of then we can define vectors which correspond to segments of this polyline and put cosinus of angles between these vectors into a matrix. Generally speaking, it would be rectangular. What can we do? We can normalize those vectors. Will be rewritten like that with the products. And then, when we have some Cartesian frame reference, we can rewrite it basically like matrix product. Two matrices. This form is very helpful because we can apply linear algebra to it. I would say about two special cases of some matrices. This one from the left is a more general one, rectangular, and it doesn't code two polylines. When then we can do two identical polylines, and we will get a symmetric square matrix, which also single line. And then we can have one polyline and a vector, and then we will replace the vector as much as we want, and also get matrix like this. There is basic properties of these matrices. So since they are assigned, all values lay in a range between -1 and 1. Also for COP matrix, mainly diagonal consists of ones. Also very important property that rank of the matrix equals rank of the matrix P. That means that we can get dimensionality of the polyline just by looking on the matrix. And matrix is independent of the Cartesian frame of reference. It's the same thing. I just said how to construct these matrices, but we also can decode them into polylines. I won't talk about each of them, but basically there are also properties of self-correcting. There are self-correcting behavior, so these matrices, even if they are not too matrices, but approximations or only most versions, this decoding will work. So how to represent protein complex with these matrices? We get one matrix for rotation, two for direction, and stop. And then the only thing we need is to get distance. Here is described the bundling operation. Basically, it's the opposite. We align two molecules, and then we start to shift one from another until under various radii stop to mess with each other. So to compare matrices, we prefer to use structure similarity index measure. It is better than most of the purely matrix norms or something. Looks very well, works very well, and very here is schematically the neural networks what we built. There is two stages of training. On the first stage, we predict basically fold from amino residues. It needed to get intermediate code, which we then use to basically predict our interactions. First stage is the plot, how it looks like test. Second stage, here is a bit of overfitting, but it's not bad as it looks. Here, so conclusion, the performance what we measured for test set is a total of 51%. If you wonder for training set, it's 70%, so 20% of the video. It's a quite good result. One can say we propose new representation, brand new. We investigated its properties. I think there is space for further investigation, but see. And we representation is very useful. For example, not just to encode for neural networks, but also for visualization. There is quite good textures on these images, and animation from the second slide was made without any physical validation, only with these matrices. And we developed and trained them. Thanks for your attention.
Okay, thank you very much, Andrew. Do you have any questions? Yeah, please.
From the point of view of physics, to describe interaction of two molecules, I must know potential of interaction. But you, maybe I missed something in your explanation. Will you give some details on interaction and energy of interaction?
Usually in prediction of interaction, we do not calculate the energies. If we want and we predict some model, then we can after take Rosetta and calculate these energies. But just predicting with neural networks, we just predict something what neural network will tell us, and then we will do whatever we can. So we do not calculate energies while predicting.
If I understand correctly, you will put it in data set.
Energy. No, because our data set we have experimentally defined respiratory structures, and we work mostly geometrically.
So they tried just to when they found some orientation, then they tried to move the complexes along some axis which they have found, just to satisfy van der Waals radius. And this is like what the maximal shift is they are doing. But they do not estimate this, not affinity, not binding at this moment. This model wasn't there. Yes. Okay. Are there any other questions? No. Okay, thank you very much, Antonio. So we finished our session. It was we have listened all the planned presentations. So I would like to say that it was quite interesting, and everything was done according to our plan. So I would like to thank all our presenters and also people who participated in these sections. So thank you very much for that. So this is I would like to say the program for today is like finished, and next we can see from the program. So next session will be tomorrow, and they start from the schedule of the chairman will say correctly. So we finished for today, but for tomorrow we can say for the people we start at 10 o'clock. So at 10 o'clock for tomorrow we should schedule, and we will be happy to see you again. Okay, thank you very much. And yeah, sure. Остальное специальные люди все знают, что